Hello student, in this lecture I will discuss mathematical model of armature control DC motor. Okay, so first we discuss what is motor. Okay, what is motor means what is servo motor. Okay, so motors which are used in feedback control system are known as servo motors, and these motors are used to convert electrical signal into an angular displacement. Okay, that means these motors are used to convert electrical energy to mechanical energy. Okay, so basically they are converted electrical signal into an angular displacement. Okay, so there are some requirements of good servo motors. Okay, so first requirement is they should have linear relationship between torque and speed. Second requirement is response of servo motors should be fast, and third requirement is inertia should be low. Okay, now come to the classification of servo motor. So there are two types of servo motor. One is DC servo motor and second one is AC servo motor. Okay, and this DC servo motor is further classified into two types. First is armature controlled DC motor and second one is field controlled DC motor. Okay, so now we discuss the mathematical model, how we developed a mathematical model of armature controlled DC motor. Okay, so see, this is the schematic diagram of an armature controlled DC motor. Okay, the variables capital R suffix A and capital L suffix A represent the resistance and inductance of the armature respectively. A separate DC source supplies a constant current IF to the field winding. Okay, for armature control DC motor, field current is constant. Okay, and the motor is driving a load having inertia J and viscous friction coefficient B. Okay, so see, when the armature rotates, it develops a voltage EB which is opposite to the applied voltage. Okay, and this EMF is known as back EMF. Okay, and this EMF is proportional to the speed of the motor. Okay, so here we take, for developing mathematical model, here we take two assumptions. Okay, so first assumption is the torque developed by the motor is a function of the flux produced by the field current and armature current. Okay, and second assumption is when armature rotates, it develops a voltage EB which is opposite to the applied voltage EA, and this EMF is known as back EMF. Okay, so see, here this back EMF is proportional to the speed of the motor and the flux created by field current. Okay, since the field current is kept constant, therefore this back EMF is proportional to the speed n, and it can be expressed by EB equal to KB into n. Okay, or this is equivalent to KB into omega. Okay, and this omega is equal to d theta dt. Okay, and where KB is back EMF constant and theta is angular displacement, and the unit of theta is radian. Okay, now if we applying Laplace transform with zero initial condition, then this equation this means 1.217 equation is equal to, after applying Laplace transform, this EB is converted capital EV as, okay, this is frequency domain equation. So after applying Laplace transform, this EB is equal to KB into S into theta S. Now the differential equation, now see the differential equation of the armature circuit. See the left side circuit. So from this circuit we can write this equation. This equation means 1.219 equation, where we can we write EA equal to LA DIA DT plus RAIA plus EB. Okay. Now here we apply Laplace transform on both sides of this equation of 1.219 equation. Then after applying Laplace transform, this equation is EAS equal to S into LA IAS plus RA IAS plus EBS. Okay. So now see the torque developed by the motor Tm is a function of the flux developed by the field current and armature current. We have already told this in assumption number 1 is this: the torque developed by the motor is a function of the flux developed by the field current and armature current. Okay, and we know the field current is constant, therefore the torque can be expressed by 1.221 equation. That means Tm equal to Kt into Ia. Okay, where Kt equal to torque constant of the motor. Kt is the torque constant of the motor and the unit is Newton meter per ampere. Okay, now here again we apply Laplace transform of 1.221 equation. So after applying Laplace transform, the equation is TMS equal to Kt into Ia of S. Okay, so this is equation number 1.222. Okay, now this torque Tm drives the mechanical load. Okay, this Tm drives the mechanical load. Okay, so this torque Tm developed by motor has to overcome inertia and friction of motor shaft. That's why we can write this Tm equal to J into d2 theta dt2 plus b d theta dt. And after applying Laplace transform, the equation will be TMS equal to J S square theta of S plus B S theta of S. Okay. So from, and this is equation number 1.223. Okay. So from equation 1.222 and equation 1.223, we can write, from these two equations we can write J d2 theta dt2 plus b d theta dt equal to Kt Ia. Okay. Now here in this equation 1.224, in this equation if we apply Laplace transform, then the equation will be this: J S square theta S plus B S theta S equal to Kt Ia of S. Okay. So in the left side, if we take common theta S, then this theta S theta S into within bracket J S square plus BS after taking the theta S common. Okay, and this is equivalent to Kt into IAS. Okay, and from this equation we can write IAS equal to theta S into J S square plus BS divided by Kt. Okay, now see, substituting equation 1.226 and equation 1.218. So see, if we substitute 1.226 in equation 1.218. Okay, equation 1.218 is this: EBS equal to KB S into theta S. So here we put the theta S. Okay, so what is the equation after substituting equation 1.226 and equation 1.218 in equation 1.220? What is our 220 equation? 220 equation equal is EAS equal to S into LA into IA of S plus RA IA of S plus EBS. Okay, so substituting equation 1.226 and equation 1.218 in equation 1.220, then the equation will be EAS equal to S into LA plus RA within first bracket, and this into JS square plus BS divided by KT into theta S and plus KB into S of theta S. Okay, so this, from this equation, if we common theta S, then after taking this term common, theta S common, the equation will be theta S into S into LA plus RA, this is first bracket, and this into JS square plus BS. Okay, and this plus KT into KB into S, and this whole term is divided by KT, and this is the equation number 1.227. Okay, so here from this equation we can write theta S by EAS equal to KT divided by J LA S cube plus, in the first bracket, RAJ plus LAB into S square plus, again in the first bracket, RAB plus KB into KT into S. Okay, and this is equation number 1.228. Okay, so this see this equation 1.228, this is the transfer function of armature control DC motor, because here see theta S is our output. Theta S is our output. Okay, because theta S is the angular displacement and EAS is our input. So what is the transfer function? Transfer function is output by input. So this is the transfer function. 1.228 is the transfer function of armature control DC motor. Okay, now if we want to simplify this equation, then see here, for simplifying this equation, here we divide the numerator and denominator by KB KT. Okay, so after dividing the numerator and denominator by KB KT, the equation is 1.229. Okay, so here again theta S by EAS, this is the transfer function, and this is equal to 1 by KB divided by this this part in the denominator. Okay, so in the denominator part is S S, and in the third bracket J LA divided by KB KT into S square plus, in the first bracket RAJ divided by KB KT plus LAB divided by KB KT, this first bracket complete, and this is multiply into S plus RAB divided by KB KT plus 1. Okay, so here see, from this equation we can write theta S by EAS is equal to 1 by KB divided by S into T alpha into Tm into S square plus, within first bracket Tm plus R into T alpha, this whole into S plus R plus 1. Okay, so in this equation T alpha is represented by LA by RA, and Tm is represented JRA divided by KB KT, and R equal to RAB divided by KB KT. Okay, so from this all this equation, using all this equation, we draw the block diagram of the armature control DC motor. So this block diagram we draw this block diagram by using all this equation. Okay, so today here I will stop here. So you people will try mathematical model. You try develop a mathematical model of field control DC motor, and you remember in the field control DC motor, in the field control DC motor, armature part is constant, means armature current is maintained at a constant value, and the motor is controlled by varying the field current. Okay, so you people will try to develop a mathematical model of field control DC motor. Thank you, student.